we are studying about transformers, ideal transformers so far, okay, and let us solve some problems on transformer, ideal transformers. Okay, so here is the first question. Uh, so we have a 3-winding transformer, okay, one primary and two other secondaries. Now the number of turns for these 3 coils are given as N1 equal to 100. This is N1. Then N2, this blue one, is 125 turns, and green N3 N3 is equal to 50. Okay. What else is given? These 2 resistors, these 2 are loads, and these load values are given. This is 100 ohm and this is 75 ohm. What else is given? This source voltage is not given. Instead, this current value is given. The RMS value of this current is 9 ampere. Okay, RMS. So now we have to find out all other quantities which are not given. For example, current I2, I3, then this voltage, call it V1, okay, plus, minus, whatever. Just find the RMS value of V1. So that's the question. How can we proceed? What are the basic rules governing this transformer? Now, if I call this voltage as V2, okay, you can call it plus, minus, and here V3, this is plus, this is minus. If V1 is like this, plus, minus. Before that, let us find out the dot positions, although that may not be necessary, but for our understanding, let us find out the dot positions for the 3 coils. If I put a dot here for the first coil, where should be the dot for coil 2 and coil 3? Should it be on the upper side or should it be on the lower side? For coil 2, okay. So how can we find the dot positions? One possible rule, there are multiple rules. One is that if this dotted end is positive with respect to the other end at any particular moment, then for all other coils, the corresponding dotted side at that moment should be positive. Okay, so you can find it using Lenz's law. That is one way. Another way is, if current is entering through this dot, then it will create some flux. In which direction that flux will be? In this case, if you apply right hand rule, that flux will be in the clockwise direction. Okay, if current I1 is entering through this dot at any particular moment, then if current enters the dot of any other coil, that should also produce the flux in the same direction in the code. Okay, for example, in this case, the dot will be here, so that if the current is entering this dot, okay, then in which direction the flux will be? That will be again in the clockwise direction. Okay, so current entering a dot in the first coil here is producing the flux in clockwise direction. Current entering the dot of the second coil should also produce the flux in the same direction, that means the clockwise direction. So the dot should be here. Similarly, for the third coil, the dot should be again here in the upward side. So now once we know all these dot positions, then for an ideal transformer, this rule V1 divided by N1 should be equal to V2 divided by N2 should be equal to V3 divided by N3. Do you know why is that so? Okay, so I'm talking about phasor voltages. Okay, so why is this rule correct? Because V1 is basically, so if I write in functional form, V1t is ddt of time derivative of N1 times the flux. Okay, now we are assuming same amount of flux is going through all the three coils, which is not exactly true practically, but that is the assumption we make for ideal transformers, that the flux is common for all the coils. Okay, same flux is going through all the coils. So this is V1. Similarly, V2 is ddt of N2 times phi, and so is V3, that is ddt of N3 times phi. So you can see that the RMS value of V1, V2 and V3, they are in the ratio of N1, N2 times N3. So this is one rule, one equation for this transformer. What else can we say? Okay, other than that, we have the MMF balance condition, which requires that the total MMF I1 N1, these are all phasors, plus I2 N2 plus I3 N3, this should sum up to equal to 0. Why is that so? I mean, if I write this equation in terms of functional forms, it means I1t N1 plus I2t N2 plus I3t N3 equal to 0. Why is that so? Because, can anyone explain this? Why is it required? Anyone would like to try? No one? Okay, so suppose when these loads are not there, okay, under no load, when secondaries are open, then under no load, how much is this current I1? How much is I1 under no load? This should be equal to V1 by j omega L1. L1 is the inductance of the first coil, and this should be equal to 0 for ideal transformer, because L1, which is proportional to the permeability of the core, okay, this should be very high, tending to infinity. That's the assumption we make for ideal transformers. So under no load, there is no current, okay, or negligible current, you can say. But does that mean phi is 0? Is phi equal to 0 under no load? Anyone? Is it possible that phi is 0? The answer is no. Why not? Because if phi is 0, then that will imply the voltage V1 is equal to 0. Because basically V1 is derivative of phi multiplied by N1. So, but V1 is not 0, so phi cannot be 0. So, can anyone explain how phi is not 0 while I is 0? Because this is because phi is equal to L1 times I1, if I write in terms of phasor quantities. So let me write, or if let me write in functional form, either is okay. So phi t is L1 times it. Now L1 tends to infinity, I tends to 0, phi need not be 0. Product of a very large number and a small number can be a finite number. So this is finite, this is finite, a finite number, this is infinite, tending to infinity, and this is close to 0. So that's okay. So phi is not 0, but current is 0. This is under no load. Now when these loads are applied, then what happens? Can phi change? When loaded, that means impedances are connected, can phi change? Anyone? Should phi change? Should phi change significantly? No one? The answer is no. Phi should not change. Phi should not change much, at least. Because if phi changes, then V1 should change. Because V1 is basically a derivative of phi times N1. Since V1 is constant, phi should remain constant. Okay, so phi should remain constant, but now we have currents I2 and I3 flowing, which were previously 0 under no load, but now I2 and I3 are non-zero, and I1 was also approximately equal to 0 under no load. So now, but now I1 need not be equal to 0. What should happen is that the MMF for I2, I3 and I1, they should all cancel each other. The total MMF should cancel so that there is no further increase or decrease of flux. Flux should remain same. Okay, so therefore, so this is the MMF produced by coil 1, current 1, this is the MMF produced by coil 2, and this is for the coil 3. Okay, so if we basically, flux is what? Flux is MMF by approximately MMF by reluctance of the core. So if I divide all these quantities by reluctance, I will get the flux, and that flux should not change. So therefore, this quantity should be equal to 0. Okay, so I have these two equations, which so we call it equation number 2, and this is equation number 1. These two together will help me to solve this question. Okay, so so let me solve it. For that, let me make a copy of this circuit. Okay, so now V2 by V3 is equal to, that should be equal to 125 by 50 N2 by N3, but V2 is also equal to I2 times 100 ohm, and these are phasors, and V3 is 75 times 75 times I3. Okay, I2 and I3 are unknowns, so this equation has two unknowns, and then I1 times 100 plus I2 times N2 is 125 plus I3 times 75, this should be equal to 0. So we have two equations, 1 and 2. There are two unknowns. I1 is given equal to 9 ampere. Okay, so you can find how much is I2 and I3 from this. So how much that will be? Anyone? If you solve, okay, you can solve it. So according to my calculation, I2 comes out approximately equal to 6 ampere, and I3 approximately 3.2 ampere. And now can you also find out how much is V1? Once you know I2 or I3, then you put it here. Okay, so then you know how much is V2. So V2 will therefore be 6 ampere multiplied by 100, so 600 volt, and then V1 will be N1 times V2 by N2. Okay, and that according to my calculation is around 475 volt. Okay, fine, I guess. And yeah. So any question here so far?
Sir, please explain the flux part.
You mean why this equation 2 is correct?
No, sir. Under no load and under load.
Yeah, yeah. Okay, so let me tell once again. So under no load, so that means this is not connected, and then I2 equal to 0, I3 equal to 0. Okay. Now V1 is a finite value. Okay, non-zero, non-infinite, some number V1 is there. So to get now under no load, let me write here. Under no load, V1, if I write in the form of a function, is equal to N1 d phi dt. Okay, so since V1 is a finite quantity, phi should also be a finite quantity. Phi cannot be 0, it cannot be infinite. Okay, because left hand side is finite. Right? So that is the value of phi. Now the point is, even when these loads are connected, this phi must remain same, because this is also true under load. So because this is true even under load. So phi therefore cannot change, because V1 is not changing. V1 is the same supply that we had even without load. So therefore phi should remain the same. Okay? But under no load, when I2 was 0 and I3 was 0, then how much was I1? I1 was also equal to 0, because under no load, look at this, since L1 is very high, V1 is finite, I1 is approximately equal to 0. So that means under no load, all currents are 0. Okay? Actually I1 is not 0, close to 0, but very small. Okay? So we take it as 0. Then when we connect this load, then I2 is no longer 0, I3 is also no longer 0. Okay? Now I2 is flowing, I3 is flowing, and I1, will it remain as before or can it change? We don't know. Let us see. The point is that now I2 multiplied by N2, okay, so I2 N2, where do I write? Okay, I'm just telling. So I2 times N2 is an MMF, is a cause which will try to create some flux. In which direction? That depends on the direction of I2. If I2 is in this direction going, then it will try to create a flux in this direction according to right hand rule. And how much will be that flux? That depends on I2 N2. Larger the I2, more will be this flux. So this will try to generate some flux. Similarly, I3 will also try to generate a flux, and in which direction that will be? Again, if it is going away from the dot, then that will be, I have made a mistake actually here. Yeah, okay, I'll also correct that. Okay, so that will also try to generate a flux which is in the anti-clockwise direction, and that is proportional to I3 N3. Actually, how much? I3 N3 by reluctance of the core. That is the amount of flux. Okay, in this case also and I2N2 by the reluctance of the core, that is the flux generated by the current I2. And these two are all in anti-clockwise direction. Okay, and now I1 was previously 0. Now suppose this is non-zero, so this will create some flux in this case, since I am assuming it to be entering the dot, so it will create flux in the clockwise direction according to right hand rule. And how much will be that? That will be equal to I1 N1 by the reluctance of the core. Okay, so now two of them are in anti-clockwise direction, one is in the clockwise direction. So let me actually put minus signs here according to the directions I have chosen. So this is the net extra flux generated under load. So this is the extra flux, but there should not be any extra flux, because if there is any extra flux, or if the flux amount changes, then V1 should also change, but V1 is not changed. Since V1 is not changed, then this extra flux should be equal to 0. That is the condition we need, okay, with proper minus signs. Okay, minus because these two currents I2 and I3, they are leaving the dots and I1 is entering the dots, so they will produce flux in opposite directions. Okay, so I had a mistake here, this should be negative. Yeah, and this is the equation we need. Okay, yeah, is it fine now?
Yes, sir.
Yeah, let me clean it up. Yeah. Okay, so I have taken long enough time, but it's okay. So next, let us take one more question. Okay, so here is a circuit. We have an ideal transformer N1 by N2, and N1 by N2, this ratio is given, so N1 is given to be equal to 200 and N2 is 100. Okay, now what else? This voltage, supply voltage is 200 volt RMS, and X is 12 ohm, so this is J12 ohm. Let me write here. This impedance load RL is 4 ohm. Okay, and we have to solve this circuit. We have to find out these two currents, everything. Yeah, so we have to solve this circuit. How do we solve it? We have an ideal transformer, and there is a primary circuit, there is a secondary circuit. So as we discussed in Tuesday's class, what we can do, we can basically transform either the secondary circuit into primary side or the primary to the secondary side and remove the transformer, and that way we can do it. So let me transform the secondary circuit to the primary side. So the equivalent circuit will be like this. So this is the primary circuit, which will remain as it is, 200 volt RMS, and this is J12. And now if I bring the secondary circuit to the primary side, what do I have to do? I have to multiply all the secondary impedances by N1 by N2 whole square. So that means 4 ohm multiplied by N1 by N2 is 2, so 2 square. Okay, and then we connect it directly to the primary circuit. So this is the equivalent circuit, and then this current, this was I1. Okay, so how much will be I1? So that will be 200 by 12, so 200 by 16 plus J12. You can find out how much is this. This is in ampere. That will be the value of I1. Okay, and so this current is flowing through this. Okay, but how much is the value of I2? Notice that we have actually changed the secondary circuit. We have changed the secondary circuit. Okay, so the current that is flowing here, which is I1, is not same as the actual current I2. But how much will be I2? I2 will be, once you know this value of I1, you can get it I1 multiplied by N1 by N2 in this way. Okay, that is one way. Another way is if I transform the primary circuit into the secondary side. Okay, so then what do I have to do? So now this is the primary circuit. This was 200 volt. This was 12 J ohm. But now I want to bring it to the secondary side. For that, I will have to multiply the voltage by N2 by N1, that is 1 by 2. Okay, and this impedance is to be multiplied by N2 by N1 whole square, that means half square. Okay, that is the transformed, the primary circuit referred to the secondary side. And then I will keep the secondary side as it is. Okay, then you connect it directly. This current I2, this is I2. How much is I2? I2 will be 200 by 2, so this is 100 divided by, this is 3J plus 4, 4 plus J3 ampere. Okay, so that will be the value of I2. And once you get the value of I2, then you can get the value of I1 as N2 by N1 multiplied by I1. Any question here? I hope it's fine.
No questions, sir.
Okay. Achha, so now let us. So far we have seen transformers with two windings. Okay, like this is one transformer with two windings. Then we saw a transformer with three windings, and we can have transformer with many more windings. But it is also possible to have transformers with only one winding, only one coil. Okay, so let us see such an example. Okay. Just a second. Okay, so here you see we have only one coil. Okay, and so you may think actually this is like this. Here we have a core, and then there is only one coil, one winding. No other coil is there. And from this single coil, we can take out various tappings. So I mean, like, it's like, in a sense, like a potential divider. Okay. For example, from here, one tapping is taken out. Then from here, so these two ends, another tapping is taken out, and then from here, and so these are various different tappings basically. And now we have a source connected here. Okay, that is this Vs, and here we have one load. This is load 2, and here we have another load 1. Okay, so, and in this case you can again find out the dot positions. So in this case, it's easy to see that all the dots for all these all the parts of this coil should be in the same side. I mean, if I consider the upper side to have the dot, then the dot should be in the upper side for all the parts of this coil. So you see we have three parts, one part, part 2, and part 3. 3 part or 3 segments of a coil. Okay, so here is the schematic, and the dots are all on the upper side, and we have 2 loads connected. Now in this case, okay, so if I call this voltage as Vs, V1, V2, and suppose this is V3, and suppose these turns are N1, N2, and N3, what should be the relation between the voltages? Anyone? These are phasors. Anyone? V1 by N1 equal to V2 by, in this case I have let me make it 3, and sorry, this is 2, and this is 3. Then V2 by N2 equal to V3 by N3. Why is that so? The reason is very same as before, because we have a flux, common flux going through all the coils, and basically V1 is N1 times d phi dt, V2 is N2 d phi dt, so their ratio should be same as the ratios of N1, N2, N3. And once again, now if I call say, one more thing here, this should be equal to Vs by
N2 plus N3.
N2 plus N3. Yes. And then if I write the currents in these segments as, okay, suppose this is I1, this is I2, and this is I3. Okay, and all currents are flowing from the dotted side to the non-dotted side in the respective section. So what should be the other governing equation for this transformer? I1 N1 plus I2 N2 plus I3 N3 should be equal to 0. Total MMF is 0. Okay, and I have taken all the currents flowing from the dotted side, so all this should be positive here, plus, 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 add them up. Okay, now in this question what is given? What is given is Vs is 600 volt, V1 is 300 volt, V2 is also 300 volt. We have to find the current in these 3 sections of the coil. Okay, AB, BC, CD in these three sections, how much is the current. So basically we have to find out how much is I1, I2 and I3. Okay, what else is given? Yeah, also load 1, so this load 1, this is this consumes 700 kVA, okay, and load 2 consumes, so this one consumes 200 kVA, okay, so this is given. Okay, so yeah, now we have to find out I1, I2 and I3. Anyone, can anyone guide me? First, so this voltage is 600, okay, V1 is 300, V2 is also 300 volt. So how much is V3? V3 300.
300.
Okay, so then how much is I1? Load 1 consumes 700 kVA, so therefore I1, the magnitude of I1, okay, this should be equal to 700 K by total voltage is 900 volt. Okay, so this comes out to be 778 ampere. Okay, acha, similarly I2, how much should be I2? Acha, now to make this problem easy for it is not necessary, but to make it easy, assume unity power factor for all loads. Okay, for all loads. Okay, it is not necessary, but to make it easy, let us assume. Okay, so then how much is the current here? Anyone? So how much is the total kVA? 600 plus 200, 900. Okay, and since we are assuming unity power factor, so that means that is 900 kilowatt. This voltage is given, so you can find out how much is this current. That will be 900 K divided by 600 volt. So this will be 9 by 6 kilo ampere here. Okay, and then how much is this current here? Acha, no, before that, how much is, let me use a different color, how much is the current here?
200 kV divided by 300.
Right, okay, so, right, so 2000 by 3, okay, so, I don't have space for writing, okay, so, let me call it I2 here, okay, then I2 is 200 K by 300 ampere, so that is 667 ampere. Okay, now so this current I1 we have already found, okay, but actually this I1 is this one, this current through the load. So this I1, I mean here this I should put a minus because this is in the opposite direction. Okay, acha. Then this I2 is flowing like this. Okay, acha. Now maybe I should make another copy of this circuit and do it cleanly. Let me do that. Okay. Yeah. Okay. So let me. So far we have found, if I call this current IAB from A to B. Okay. So we have got IAB equal to minus 778 ampere, and this current, if it is I2 is 667 ampere. Achha. And then what else can we find? Achha. Let me call this IBC and this as ICD. Okay, we have also found this current. Okay, so now we can write so applying KCL at this node, we can write IAB is in this direction. So this, how much is this source current? We found 9000 by 6 kiloampere. Okay, so we can write 9 by 6000 ampere. This is equal to minus IAB and plus IBC. So from this we will get IBC is how much. So from that we can get IBC is equal to how much. Okay, so we know IBC, we know IAB. What is left? ICD. Okay, also we can use KCL at this node, node C. So from that we can write ICD is equal to IBC. We already know how much is IBC, and minus I2. Okay, all this this is already known, so we already also know this. Now I will leave it as an exercise for you, homework. Check whether IAB multiplied by what is the turns ratio for AB, BC and CD portions. So all these are equal because 300 volt, 300 volt and 300 volt. So let's check whether IAB times 300 plus IBC times 300 plus ICD times 300 is equal to 0 or not. That should happen. Okay. So any question here for this problem? No? Okay. So then let me take one more example. Okay, acha. So in this question we have a two-winding transformer and the it is given that this N1 is 1600, N2 this is 400, and N3 is 100. Okay, acha. Then Z2, this impedance is given 50 plus J80, and Z3 is said to be a 100 kilowatt resistive load. Vs supply is given 5 kilovolt. Okay, we have to find out how much is this primary current. Okay, and what else? So question is, how much is I1? How much is input power? And yeah, so these two are the questions. Okay, so how can we solve it?
IK divided by 1 1600 is equals to V2 divided by V2 plus V2
Voice is not coming clearly, so let me tell. Okay, so Vs is 1600 volt, and okay, also let me give you the dots, otherwise it's incomplete. Okay, so dots are like this for these three segments. Okay, now so if this voltage is V2 plus minus, then V2 is how much? This will be 5000 by 1600 into 400. Okay, so you can calculate how much is V2. Then yeah, right. And then if this current is I2, okay, I2 will be how much? V2 by Z2. Both V2 and Z2 are given, so you can also find out how much is I2. Then if V3 is the total voltage, okay, how much is V3 across Z3? That will be 5000 by 1600 into total transmission is 500. So you can also find out how much is V3. Then this current, if I call it I3, okay, how much will be I3? That will be V3 by Z3. This also you can find out. Now you know I2, I3. Okay, what's next? Acha. Now we use.
Sir, I think will be found by the power request.
Yeah, you can also use. Oh, yeah, you're right. Yeah. So Z3 is not given. You're right. So since Z3 is not given, okay, so we cannot do it in this way. You're right. But V3 is known, unity power factor. So I3 will be the 1000 kilowatt divided by this voltage V3. Okay, this way we can find out, because Z3 value is not given. You are right. Now, Now once we know I3, I2, then we can use MMF balance. Okay. So what will be the MMF balance equation? Yeah, this is a bit tricky. Can you tell me what is the MMF produced by I1? If this is turns, number of turns is N1, how much MMF is produced by I1? I1 N1. And I take it to be positive because it is entering the dot. Let me take that positive. Now, if so, how much is the MMF produced by this portion of the coil? How much current is flowing here? Okay, how much is the current here? That is I2 plus I3. Okay, so and this current is going away from the dot. So I write minus I2 plus I3 multiplied by this portion N2. Okay, and then consider the lower part, N3 part. Okay, how much is the current here? Here the current is I3 going upwards. Okay, so this is again going out from the dot. So I again use minus sign, minus N3 I3. Now I2 known as, and this total should be equal to 0. Now I2 known, I3 known, so from this you can get how much is I1. Right? And once you know I1, then you can get the input power. So input power, let me write complex power, complex input power, that will be Vs I1 star, and the real part will be the active power. Okay.
Sir, please explain the MF part.
MMF part. Yeah. So I1 current is entering the dot, and this first coil has N1 number of turns. So I am taking MMF as positive because I'm taking the because the current is entering the dot, and I1 N1 is the corresponding MMF. Now consider the upper part of this second coil. How much is the current here? I2 plus I3. Using KCL at this point, I2 plus I3 is the current going upwards. That means it is going out from the dot. Since it's going out, so I use minus, and current is I2 plus I3, number of turns is N2. Okay. Achha, now you consider the lower part of this second coil. Here the current is how much? I3. Okay, because this current is I3. And number of turns is N3. So I3 N3 is the MMF, and negative because it is going out from the dot. So this is the total MMF, that should be equal to 0. That's it. Yeah. Is it okay?
Yes, sir.
Sir, then according to this convention, would the flux at any point due to the current in that transformer be 0?
Yeah. So basically,
Like if we see it as a KVL, then would there be a KCL also?
Yeah. So according to this, the flux in the transformer should be 0. But this is actually the flux, extra flux, excess flux after the no load flux. Okay. So this is one thing you have to understand. I believe this is one very confusing part about the transformer. Okay. So let me explain that once again using this part, this circuit only. Okay. And hopefully I have to stop after this because time is running out. Okay. So first, assume these two are not connected. Okay. Let me write in detail. When no loads are connected. Okay, so the code of the transformer is here, and okay, so so there are two coils, one on the primary side and one on the secondary side. Can you visualize it? Let me try once again drawing it. okay, I hope you can, so there are two sides of this code, and left side has n1 number of turns, right side has n2 plus n3 number of turns. Now, current in the second coil is 0 when there is no load connected, okay? And some current is flowing, call that in the primary circuit, call that I10. I10, now primary current is I10. Is I10 equal to 0? Is it exactly equal to 0? No. How much is it? This is equal to basically supply voltage divided by j omega L1. And this is approximately equal to 0 because L1 is very high. Then,
Yes.
now we connect loads. Okay, so now we connect the two loads, and so therefore here we have current I2 flowing and here current I3 flowing, and I1 will also change. And suppose I1 becomes this previous current plus call it I11. Okay, this together is the net current I1. Okay, now, so we have all these three currents flowing. Acha, before that, before connecting the load, how much was the flux? So this I will come later. Before that, so flux, call it no load flux. Okay, that is phi is given by how much? I10 N1 plus 0 into N2, because 0 into N2 plus N3, because no current is flowing in the secondary coil. So that's why 0. So this is the total MMF divided by the reluctance of the coil. That is the flux. Then
Yes.
now when we connect the loads, now on load flux okay, is how much? I1 N1 plus N2 multiplied by here how much is the current in N2? 2 plus I2 plus I3.
I2 plus I3.
Okay, these are phasors, and plus N3 into I3 whole divided by the reluctance. Okay, and this flux must be same as no load flux. Why the no load flux and on load flux should be same? Because the derivative of the flux is the supply voltage, and supply voltage is same under no load as well as on load. So therefore the flux should also remain same. Okay, so therefore no load flux and on load flux, they are same. So thus I can write this quantity copy paste, and this quantity copy paste. Let me write it here. So these two quantities should be equal to each other, but right hand side is same as if I break I1 into I10 N1 plus I11 N1 plus into this is 2. This is 2 plus 3 plus N3 I3 whole divided by the reluctance. One thing is common on both the sides, which is this first term. Okay, so this term and this term, they are same. Okay, so therefore this is basically the excess flux. This is basically the excess flux. This should be equal to 0. This is the extra flux. This is
Yes,
the,
sir. Got it.
yeah. But now I11 is approximately equal to I1,
I1.
itself, because I10 is small.
Less.
That's the yeah. Okay, yeah, I have to stop here. It's already 5 o'clock. I should stop.